In today's lesson, we're going to be looking at the difference between linear functions and nonlinear functions. We've been working with linear functions, but we haven't really discussed what it means to be linear. The definition of a linear function is a function in which the rate of change is constant. What that means is, when you graph an equation, it might be increasing or decreasing, and the rate at which it increases or decreases stays the same. This means that the graph for all linear functions will be a straight line because it is increasing at the same rate each time. So, as you can imagine, a nonlinear function is the opposite of a linear function. The definition is a function in which the rate of change is not constant. Therefore, the graph is not a straight line. Maybe you have a graph that is increasing at this rate, and then all of a sudden it starts to spike way up. So this is not a straight line. Or maybe you have a graph that starts to decrease, and then over time, it starts to increase back up. So these would be examples of nonlinear functions. Now, there are many ways to determine whether a function is linear or not, and one of the ways is trying to find if there is a constant rate of change. And how we do this is you look at how the y values are changing, and then you look at how the x values are changing, and you divide. An easier way to write this, I like to just do a triangle means the word change. So it's the change in our y values divided by the change in our x values. When you do this, if you get the same number every time with all of the ordered pairs that you have, that means you have a constant rate of change. So here we have a table of values, x values and y values that create ordered pairs. We need to test, is it linear or not? And the way you do that, you have to test, is the rate of change constant? And remember, to find the rate of change, we have to find the change in our y values divided by the change in our x values. So let's first look at the y values. From 50 to 35, it's going down by 15. From 35 to 20, it's going down by 15. From 20 to 5, down by 15. And 5 to negative 10, it's down by 15. So this looks pretty constant, but that doesn't mean it's linear yet. We still have to find the change in our x values. From 2 to 4 goes up by 2, 4 to 6 up by 2, 6 to 8 up by 2, and from 8 to 10 up by 2. So the change in y divided by the change in x. My y values are changing by negative 15, and my x values are changing by 2. And as you can see, that's going to be the same for each one. So, because the rate of change is constant, this is an example of a linear function with the rate of change of, you can leave it as negative 15 over 2, or you can change it to negative 7.5. Here is example number 2, a table of values, x and y, and we have to determine, does this represent a linear function or a nonlinear function? And that is determining whether or not it has a constant rate of change. So, rate of change, let's figure out how our y values change. It goes up by 6, then up by 3, up by 6, and then up by 3. So there's a pattern, but it's not constant, but you can't determine if it's linear just from the y values. You still have to look at the x values. Goes up by 3, up by 3, up by 3, and up by 3. up by 3 each time. So, the change in y divided by the change in x. Let's look. First we have the change in y is 6 divided by the change in 3, or the change in x, which is 3. And then the next one, we have 3 divided by 3. And it's pretty obvious that 6 divided by 3 does not equal 3 divided by 3. Therefore, this is clearly a non-linear function. It does not have a constant rate of change. Here we have example number 3. Y values, let's see, the first ones they change by 3, go up by 3. Then it goes up by 5. Then by 7. And then it goes up by 9. And then my x values go up by 1 each time. So my change in y divided by my change in x, let's see, change in y, 3, divided by my change in x, 1, is obvious that it does not equal this change in y, 5, divided by this change in x, 1. So the rate of change is not constant, and here is an example of another non-linear function. Okay, here's our last example where we have a table of values that we have to determine whether or not it is linear. So let's find the change in our y values. This goes down by 4, down by 4, down by 4, and then this one goes down by 8. Alright, well let's check out our x values. It goes up by 5, 5, 5, and then it goes up by 10. So let's think about this. Change in y divided by change in x. It looks different, but let's check this out. You have negative 4 divided by 5, the change in y divided by the change in x. And that is the same for the next two. And then we have negative 8 divided by 10. Negative 8 divided by 10, which looks different, but if you reduce that fraction, you're back to negative 4/5. So even though this looks different, it is actually the same rate of change. So this is a linear function with the rate of change of negative 4/5. Now we're going to practice graphing linear functions and the nonlinear function, the specific one, the quadratic function. So linear function, this is just a quick review. Make an XY table. You want to get varied points, so pick values for x. Let's do -2, -1, 0, 1, and 2. If you plug in for x, 2 times -2 is -4, minus 5 is -9. -2, -9. Plug in -1, 2 times -1 is -2, minus 5 is -7. Plug in 0, 2 times 0 is 0, minus 5 is -5. Plug in 1, 2 times 1 is 2, minus 5 is -3. And then plug in 2, 2 times 2 is 4, minus 5 is -1. So now if we connect these and you can extend the line, here's the graph of this linear equation, and notice that it is a straight line. So we often as a joke call it the linear function. In this example, we're going to graph a nonlinear function, and in this lesson we're only going to focus on a quadratic, because there are lots and lots of different nonlinear functions, and quadratic is just one of them. Quadratic is when you have an exponent of 2 in your equation. So if we graph this, it's not going to be a straight line anymore, and actually every quadratic creates a horseshoe, and they either open up or they open down. So, same idea, make an XY table using negative values and positive values. So you plug them in for x squared minus 3. So when you plug it in, make sure in parentheses you have negative 3 squared minus 3. And those parentheses are important because negative 3 squared is a positive 9, and 9 minus 3 is 6. So negative 3 up 6. And now plug in negative 1. Negative 1 squared minus 3. Negative 1 squared is a positive 1, minus 3 is a negative 2. So negative 1, negative 2. If you plug in 0, 0 squared is just 0, minus 3 is negative 3. If you plug in 1, 1 squared is 1, minus 3 is negative 2 again. So here we have the same number showing up again. Over 1, down 2. And then the last one, 3. 3 squared is 9, minus 3 is 6. So we go right 3 up 6. So notice how this 6 shows up again. So if you connect these, you will get a curved horseshoe, just like that. So there is an example of graphing a non-linear function. So the biggest thing is linear functions have a constant rate of change and non-linear functions do not. Good luck with the lesson.